one of my most recent videos, I showcased how you can replace tool steel with plastic by 3D printing your own ER32 tapping collets. And that worked way better than I ever could expected. So this time we're up in the ante, swapping out 100 pounds of cast iron for about 20 bucks worth of plastic. You're gonna wanna stick around for this. We are attempting, and I cannot emphasize that word enough, attempting to 3D print our own rotary fixture table. It's all in the name. It's a table you can fixture your parts to, and it rotates. That by itself is basically useless, but if you slap it onto a milling machine table, all of a sudden you have a precise and accurate way to cut circles, and well, circles into steel and aluminum. Rotary tables can do a bunch of other stuff, but we're not gonna get into any of that today. Okay, but like why? Why not just buy one? You know, sort of like a normal person would? There has to be a reason why no one has ever done this before. Are you really gonna sink a bunch of time and money into a project that will most likely fail? Yes. Yes, I am. And the reason why I'm gonna do this, well, it's complicated, but not complicated. It's the usual bag of delusion, costs money, too big and heavy, and the traditional ones take forever to set up. That last one is the real killer, as if something is difficult to set up, I'm just never gonna use it. But that all changed when I saw Inheritance Machining's Rotary Fixture table build video. If you haven't seen his, well, I don't know what you're doing down here at the bottom of the barrel. His build ditches all those typical inconveniences to the point where even someone as lazy as me will have no excuse not to use it. There is a problem though. His build requires a rotary table to, well, make the rotary table. That and a bunch of other tools I do not have, but like I said, my ER collet video worked out pretty good. So I was kind of like, maybe we just 3D print one? We're gonna find out. With the design stolen, we can jump straight into 3D printing. Now, for me, it's all about the looks, so we're gonna keep the spaghetti in the corner and we're gonna break out the sauce. Probably a bad idea, but for this project, I really wanted to use Soriatec's Sculpt Clear Resin. And I say wanted to, because all of my test prints just kept coming out wonky and weird. Tolerances are all over the place, features are drooping, bizarre surface artifacts. I'm pulling my hair out trying to figure out what is going on, why? Eventually I just give up. I'm like, let's just use a resin I actually know works. Tried and true, something accurate and precise, and same problem. Okay, maybe it's the batch. Let's get a new bottle. I know this stuff works. Nope, same problem. Orientation, change that up. Nope, same problem. FEP sheet, that thing's really old. We replaced that, it's gotta be fixed. Nope, same problem. At this point, I don't even know what to check anymore. My last idea is maybe the LCD screen is messed up. Test that, and yep. Sure enough, there's your problem. A whole bunch of dead pixels. Most likely from supports breaking off during a print, getting stuck in the vat, not getting cleaned out, and then on the subsequent print, the bed comes down and crushes them into the LCD screen. So there went $100, but honestly, I don't even really care about the money because at this point, my pain had only started to begin. Let me explain. To replace the LCD screen on this printer, and I'll remind you, this is a consumable item, something you're supposed to eventually do, requires you to disassemble, and I mean this literally, the entire printer. The entire thing. From stem to stern. Why on earth? It wouldn't even be this bad if it wasn't for the fact that this printer is supposed to have detection software that actually is supposed to stop this exact thing. Honestly, it is my fault in the end of the day. I should have checked, I should have seen if there was stuff in the vat, but it just feels so much nicer to blame others. Either way, with the machine rebuilt, we finally have a good test print. I've only been doing this in sections. This model has really been packing on the LBs. I put it on a major diet, and yet it still requires nearly an entire liter bottle of resin. Things did start to go my way though, as the final print came out looking gorgeous, or at least I hope this is the final print. Fingers crossed. After that, I threw in a bunch of threaded inserts. If you want to know how I install threaded inserts into my resin prints, check out my other video below. Next up, sanding. I was about halfway through sanding when I realized, what are you doing, Michael? You need to actually test this thing before you sink any more time into it. There is one more part though that we need to make though before we can test. The center arbor, which luckily means we get to do some honest to God machining, or at least I thought I was lucky. The center arbor is a really basic part. It's just 3 diameters and a thread on the end. We're gonna have our mill pull double duty as a lathe, and already a problem. I cut the stock too short and there's not enough engagement into the ER collet. Round 2 went smoother, but I am picking up a little bit of a taper. Perfect example of why you really shouldn't use a mill as a lathe. But a little bit of emery cloth and some sanding, and we can dial that taper out and get the fit just right. Well, it's a little easier said than done though, because this is actually my 3rd attempt. The first one was slightly too loose, the second one was way too loose, and the third one I actually took my time and pretty much nailed it. Now we aren't done because I decided to make this a 2-piece deal, mostly because turning 1 inch of steel is way harder than turning 1 inch of brass. But I made a mistake again. When I was pressing on the arbor, the thing wiggled all over the place, leading to a very loose connection. Some liquid persuasion in the form of Loctite though fixed that issue real quick. Final step, we need a precision bore in the top for an alignment pin. Again, should be a simple task, one that I managed to mess up over and over again. Turns out my vise was loose. I mean, it looked tight, it felt tight, it even smelled tight. But these grinding vices, they can be a bit deceiving when they get stuck in between indexing slots. So after a literal clown car's worth of mistakes, the part is done. Oh, fake out. I added a couple holes to the top for a spanner wrench. And now we can do a quick assembly and actually test this thing. All this work could be headed straight for the trash. I really hope not though. Setup for the rotary table was pretty straightforward. A pair of internal cap screws connected to the T-slots in the middle table. We then plop our material down onto that center alignment pin and then death grip it in place with some teeny tiny little strap clamps, which are honestly my biggest worry about the whole thing. Before I forget, our material we're cutting is 3/8 aluminum tooling plate getting smacked in the face by a 3/8 high-speed steel end mill roughing style. So pretty much as light duty as it's ever going to get. Still, I'm taking it easy at first with only about 1 thou, oh no, not 1 thou, 10 thou step over. 1 thou would be a little too light. And much to my surprise, it's going pretty good. Yeah, to the point where by the end I was doing a full 50 thou step over, which is certainly nothing to like shout to the masses about, but it's a good start. And we're certainly gonna really push this thing at the end. We know the thing works. Now we need to just add on all the accessories that make it work good, like these bushings, which are just an off-the-shelf part and get pressed into all the holes. The bottom of the hole is a thread, while the top of the hole is a bushing. The threads allow us to clamp our parts down to the rotary table, while the bushings, coupled with alignment pins, allow us to dial in very specific offsets to our spindle. And for the first time on the entire project, nothing actually went wrong, much to my surprise. That said, the bushings could work loose over time due to plastic creep deformation. Only time will tell. While I was at the mill, I decided I might as well run a dial indicator over this thing and satisfy my own curiosity as to how well it actually printed. And again, to my surprise, pretty darn good at only 5 thou runout, and that's straight off the printer. We can definitely improve that. The pin alignment and squareness was also pretty good at only 3 thou variation between the pins. Now, to try and improve that run out, we're going to send a fly cutter across this face. And of course, I immediately made a mistake. Once again, forgetting to tighten something. How many times can you do that? Like, seriously. It led to a bit of tear out, but we tightened the tool up, replaced the chipped insert, did some light passes, and it cleaned up pretty decently. Although not without consequence, as it now looks like it snowed all over my parents' garage. Oh, and before I forget, the runout did improve from 5 thou to 3 thou, so I'll take it. I mean, if I had machined these parts from steel or aluminum and I was getting these numbers, I'd actually be pretty depressed. But for the fact that I just hit print and go, I'm pretty happy. The final two machined accessories that we need to make are the mounting plate and the handle. The mounting plate is actually not necessary at all. You saw earlier, god damn it. The mounting plate is actually not necessary at all. You saw earlier, we bolted the rotary table directly to the milling table using its T-slots. But this subplate makes it so we can bolt it directly into the vise. This is not only useful for quick setups, but it gives us a repeatable position. So we can take the rotary table on and off, over and over again without ever losing our alignment. Or at least that's the idea behind it. Remember, I'm stealing all of these concepts from Inheritance Machining's original build. The final machine part was the handle, which is a really basic part, like I've been saying all along, but this time everything went according to plan. It's made from 304 stainless and has 2 threads on the end, 1/4-20. The only real trick to the part is it has a chamfer on it that has to perfectly match the chamfer 3D printed into the body. This is to give it a little bit more positive engagement when screwed in. The machine parts are completely wrapped up and all we have left now are the 3D printed accessories, starting with the knob, which attaches directly to the handle we just machined. The knob is a pretty straightforward and simple 4-speed shifter design, although it's specifically based off the shifter in my 61 Corvair. The cool thing about this model though is it's fully parametric, so if you need a different size, just type it in and bada bing, bada boom, you got it. All the 3D files included in this build are going to be in the links below, so check those out. The final 2 printed parts are a pair of hard stops and the table lock. Now, I'm going to dive into exactly what these do in a little bit, but the basic idea behind them is the hard stops interact with the handle and prevent the table from over-rotating. Basically, it makes sure that every time you swing it, it goes exactly 90 degrees, or however many degrees you've dialed it into. They have a pair of fine adjust screws that make dialing it in a complete breeze. While the table lock, well, locks the table. It connects the lower and the bottom together, primarily for doing indexing and hole patterns. The coolest part of these accessories, though, is the fact that the hardware is captured, meaning you can never lose the bolts, which I have done so many times in the past. This is accomplished by doing a back relief cut on the screw and then pressing on one of these teeny tiny C-clips. The other thing I discovered on this is the fact that they actually make undersized washers specifically designed for socket head cap screws. Like, how have I not heard about these before? Okay, I promise we are so close to actually testing this thing, and believe me when I say I am far more anxious to get to that point than you are. But we do have one last step, and that's going to be finishing and assembly. For finishing though, I chose to go with black as the primary color and then the ivory / off-white as the accent color. Accents being letters, numbers, and the handle. After we do that, the whole thing gets finished with a 2K gloss clear coat for some heavy duty protection. Final assembly. Pretty straightforward. The 2 halves bolt together using the center arbor. Oh, and I don't think I've mentioned this yet, but those 2 giant bearing looking things, well, they're a pair of thrust bearings. Their job is to take up any of the downward loads acted on the table by the milling machine, while the center arbor takes up any of the side-to-side loads. And that, ladies and gentlemen, is the entire build. The only question now is whether or not it's garbage or greatness, and those are our only 2 options. Fingers crossed for greatness. Okay, finishing didn't quite go as planned. Assembly did, but not finishing. Right at the end, as I was doing the clear coat, literal seconds before I was about to call it quits, I managed to drop the part right onto my concrete floor, busting out the side. Yeah. It's how she goes, man. It's just how she goes. So, it's 3D printed, so yeah, it's not the end of the world. All we gotta do is hit a button and we get a new one, right? Well, that only works if you actually have enough resin, which I thought I did, according to the estimation I did, but it turns out it's only an estimation, because once again, right at the end, I completely ran out of resin, and well, the printed part looks pretty much as bad as the busted out part. So, I don't even care anymore. We're just going to test this thing. The damage really shouldn't affect its performance, so let's find out whether or not this thing works or not. Now, unlike the test before, this time we're going to use the pins to align the part rather than the center pin. Now, we need to offset it exactly 3/8 of an inch, so we're going to use a couple 16th inch shims, and then we got our teeny tiny little strap clamps. All right, here goes nothing, man. Let's see if this works. I really, really hope so. I just realized I'm climb milling, which is probably not the right way to do this. You know, a little bit. Whoa! Yeah, she moved. T-slots are not tight enough. You can't climb mill, Michael. You can't climb mill. God damn it. So far, so good. Forces don't feel any worse than the rougher. Yeah, baby. Making some decent chips. I can definitely feel the vibration coming through now. Oh yeah, she's vibrating a little bit. But hey, it's taking it. Yeah. Oh, look at her go. Okay, baby. Now we got something here. That looks rather respectable. Hell yes, this thing is actually working. No more stupid mistakes. It's making decent chips. It's making a mess. I'm loving it. If this is all it can do, I'll be happy. But stick around, because we're going to see what this thing can do in steel. Yeah, I don't know about this. It is not like that. Nope, it really don't like that. Yeah, no. Okay, let's try the rougher. Yeah, look at, yeah, I don't know about that. This is pretty sketchy. All right, let's try doing something else. I say I really don't like this, but it is doing it, sort of. Oh my God, it's vibrating. That's what she said. All right, switching to 1/4 inch rougher. Better. I mean, we're still vibrating, but this is way better. Nope. All right. That's too much. Pushed her luck. Light passes. Definitely seems to be its happy place. Like 10 thou? That's easy. You know, maybe this is it. You just do like really light 10 thou passes. All right. It did it. It's something. I'll take it. Cut. Ups, downs, left, rights. Well, this project has seen them all. Really goes to show you, just because something is 3D printed does not mean it's easy. And if I'm really being honest, you only got to see a small portion of the struggle that was this project. But hey, it works great-ish, and it looks great. Ish. I mean, come on. We managed to machine steel using frickin' plastic. Like, my mind is blown. And sure, it is finicky when it comes to steel. You really gotta dial in those feeds and speeds. Get the tool diameter, the RPM, and the depth of cut just right. But it will do it. And for the occasional oddball project, it's gonna be an absolute lifesaver. Now, it's not all upside though. This thing has about $150 to $200 worth of materials in it. That's a lot. For that same price, I could have easily just bought an import rotary. That and the durability of the top, well, it's questionable. It's already started to pick up the occasional scratch and ding here just from the limited testing that I've been doing. Hopefully, that just means it needs the occasional sand and reshoot. If I was going to do the project again, I would definitely add more meat to the top so that I could just deck the surface whenever it gets too dingy. The real question though is, will I ever be bothered to fix the base that busted out? Maybe, but probably not. On to the next.